Today we're going to talk about ideal gas law. It was developed so that we had all the influences of gases in one equation. How it's derived is by combining Avogadro's hypothesis, the volume of a gas is directly proportional to the number of moles of gas, with the combined gas law, which involves the relationships between temperature, pressure, and volume. To derive this, let's start with the relationship of Avogadro's hypothesis. We know through a proportionality statement that volume is directly related to the moles of the gas. So if you increase the number of moles, the volume of your gas sample increases. We also know from Charles's law that volume is directly proportional to temperature. So if the temperature goes up, the volume goes up. And we know from Boyle's law that volume is inversely related to pressure. So if pressure goes up, volume goes down. To get rid of the proportionality sign, the little fish, and make it an equal sign, we need to introduce a constant. Most people would think it's a k, but because this is a special law, the constant we introduce is actually r, and this is the first constant we're actually going to learn what the value is and use it in the equation. We're not going to do our math magic and get rid of it. So v is going to equal rnt over p. Scientists usually rearrange this equation so that it's a single line of text with no fraction. And when you do that, you often see the form, which we'll use, is PV equals nRT. Now there's only one condition on this equation. Temperature has to be in Kelvin. You also need to know what the value of R is. So let's figure that out by taking a fictitious 1 mole sample of gas at STP. If we sub in the values, at STP the pressure is 101.3 kPa. Because I have a 1 mole sample at STP, I know the volume is going to be 22.4 liters using Avogadro's molar volume shortcut. By definition, I have a 1 mole sample. Let's get lots of sigdigs on this, so we'll put 1.000. We're going to solve for R, and at STP, the temperature is 273. If you rearrange for R, I'm going to figure out what these are equal to times each other, and then divide them by 1 and divide it by 273. R equals 8.314. Now the thing is that R only equals this value if you sub in volume for liters, kPa for pressure, and Kelvin for temperature. If you use torr for pressure or mils for volume, then R is going to equal some other number. So it's always important to convert into kPa, liters, and Kelvin before using PV equals nRT so that you know what the value of R is. Let's try out example number 3. What volume would 2.32 moles of H2 gas have if held at 105.3 kPa and 25 degrees Celsius? We know a lot of gas laws, but the ideal gas law is the only one with moles, temperature, pressure, and volume in it. So I'm going to start by writing down that equation. I'm going to sub into it what I know. My pressure is 105.3 kPa. I'm looking for the volume. I've got 2.32 moles. R equals 8.314. And my temperature converted into Kelvin is going to be 298. If I rearrange and solve for volume, I'm going to get 54.6 liters. Let's try out example 4. How many moles of CO2 are there in a sample of gas with a volume of 18.2 liters at SATP? This is an important question. It highlights the fact that we can take physical properties of a gas that we can measure, like volume, its temperature, and the pressure we have the container at, and actually figure out how many particles or moles are in that container. So I start with the ideal gas law and sub in what I know. At SATP, the pressure is 100 kPa, the volume is 18.2 liters. I want to determine the amount of moles. R equals 8.314, and at SATP I'm at 25 degrees Celsius or 298 Kelvin. When I'm rearranging for N, I'm just going to take 100 times 18.2 and divide by both of these terms. That turns out to be 0.735 moles.